Let's go through just a few more examples in general to see how this works, and let's go through some of the basics of Newtonian physics. I'm sure you've covered this in your physics class. And first, I want you to think about a velocity. What are the dimensions of a velocity? Now, a big hint, I've already talked about that a little bit in this presentation, but what is the definition of velocity and how does that break down into dimensions? Well, the velocity is how something moves through space over time, and you talk about it in some sort of change in distance over time. Well, distance, that's usually specified by a length, and time is of one of the fundamental dimensions, t, and you would expect the dimensions of velocity then to be a length per time. Again, you can think about units to help with this, because if you're talking about the velocity of a car, we usually say something like miles per hour. Miles is a unit of length, hour is a unit of time. But again, if I ask for dimensions, I'm looking for length and time, not miles an hour there for that particular question. So what's acceleration? Acceleration is defined in terms of velocity, correct? So the ability to accelerate something has something to do with force and energy. And what you want to do is change a velocity in order to cause an acceleration. So to quantify acceleration, then you might say, well, that is the change in velocity over time. Well, we've got our dimensions for velocity already. We called it length per time. And we're saying, well, that's the change in velocity over time. We need another time to deal with that. So if we take length per time and divide it by another time, that's why acceleration has dimensions of length per time squared. Again, if you think about the acceleration of gravity on Earth, about 9.8 meters per second squared, again, you can think about those units to help give you hints to the dimensionality. But remember, the dimensionality is a more fundamental description of what you're talking about with acceleration, and it's independent of any other unit system. So we can keep going. Possibly one of the more famous equations in Newtonian physics is the definition of force. So hopefully you can remember what force is. And force is the idea that you're causing some mass to accelerate. You need a force to cause a mass to accelerate, or you need a force to cause a change in momentum of a mass. So the way to quantify that is to say, well, how much mass are you talking about and how much acceleration are you talking about? So F equals ma. Force is equal to mass times acceleration. Again, we know our dimensions of acceleration from before, length per time squared. Mass is just a fundamental dimension. So we now know that the dimensionality of force is mass length per time squared. Last one, let's talk a little bit about energy. We're going to talk a lot about thermal and Newtonian mechanical energy in this class. So understanding the fundamentals of what energy is pretty important too. Now, energy is a bit of an abstract concept, but we typically put it in terms of physics based on our ability to apply a force over a distance. And what that really means is the ability to do work. So energy is the ability to do work on a mass. And the way we characterize that is applying a force to that mass over some distance, force times distance. So energy and work basically have the same dimensions because we are defining energy in terms of the ability to do work. So we have our dimensions for force, mass, length per time squared. We're applying that over a distance. In this case, it's force times distance. So that L combines with the other L, and you end up with mass times the length squared per time squared. So mass, length squared per time squared are the dimensions of energy. You'll find many, many more examples of dimensionality, and through all the textbook, all variables are, the dimensions of those variables are provided, and there's a handy Appendix A in the textbook that includes a big table of unit conversions that is categorized by the dimensionality of the variables those units apply to. I know frequently when you're reading the primary literature in hydrology, so the papers and journals, you'll see the variables described in terms of their dimensionality. So this is a handy reference to make sure you understand how these dimensions work. You can see other ones here like mass density, a mass per volume. That should make sense. A weight density, a force per volume. You can see velocity and acceleration here. You see a discharge. That's an important one in hydrology. Discharge is a volume per time, so a volume of water that's moving out of the control volume per unit time.